Hello and welcome to Golden Geography. Today we're going to be thinking a little bit about hazardous earth, a debating topic from the OCR Geography A-level specification. We're going to be thinking a little bit about question 3, which is what are the main hazards generated by seismic activity? There's two parts to this and we'll look at them in turn. So first of all, 3A, there is a variety of earthquake activity and the resultant landforms and landscapes. Okay, so seismic activity and earthquakes are tied together. So we want to start by just thinking a little bit about energy waves. And there are several different types, but the main two you need to know a little bit about are P waves and S waves. They move in different waves. And if you've got a slinky at home, you can play with this because it's great to play a little bit around with that. P waves move fastest. They move in a kind of compressional wave, so they don't really kind of wobble as such. It's more kind of a movement, in-out movement, almost kind of like a hydraulic movement that you have. And because of that, they move quite quickly. And it means they travel through both solids and liquids, which will be important in a moment. S waves are much more wobbly. They move slower than P waves, but they do cause a lot more damage. Feel free to pause the video and have a little look at the differences between P waves and S waves on the table. Okay, so we talked about how they move, and you can see here the difference between S waves and P waves. Because of that compressional movement, P waves can move through different layers of the earth than S waves. S waves are relatively restricted, and you can see there's a large section that's called the S wave shadow zone, which means in those areas those S waves won't reach. Whereas P waves will move through that, they will move through the core, but will be refracted and have slightly different shapes, movement. There are two small areas that are called P shadow zones as well. But the difference is important, and the reason it's important is because both of these can be detected by seismographs. So P waves move quickly and can be detected, don't cause as much shaking, and because they're detected, they enable people to give warning. They enable scientists and governments to give warnings. It may only be 10 or 20 seconds, but it's enough for people to then know to take refuge before the S waves hit, and those S waves bring the shaking and cause the damage. A couple of other things we need to think a little bit about is the shallow and deep focus earthquakes. Well, we even have intermediate here too. So we get earthquakes, and the focus or the very center of that earthquake is really important. So here in this picture we have a subduction zone, and the area where we get that friction build up is called the Benioff zone, and where that friction then is released will impact the earthquake a little bit. So the red to the top is what we call shallow earthquakes. They cause the most damage. The yellowy green areas, there are intermediate, and then the blue areas are deep earthquakes. They cause the least amount of damage. So what about shallow focus? Well, these tend to be relatively shallow in depth. You're looking at about 70 kilometers or 43 miles down from the surface of the earth. They tend to be more destructive. There's less distance for the S and P waves to move, so less energy is dissipated, and they tend to be higher in intensity. They felt much more strongly on the ground above them. They are more common, and particularly near tectonic plate boundaries, especially within the Pacific, the Ring of Fire, they're quite frequent. Good example was a 2011 earthquake in Japan, which had quite a shallow focus of around 29 kilometers. Deep focus earthquakes, well, you're looking at earthquakes here that are about 300 kilometers to even 700 kilometers, so up to 434 miles below the surface of the Earth. These tend to happen a little bit more where you have collision zones, your continental plate boundaries. They're less destructive on the surface because that deeper release of energy has dissipated a little bit more before it reaches the surface, and they're less common. Good example is the Nepal earthquake in 2015, where the origin of that earthquake was thought to be about 650 kilometers beneath the surface of the Earth. When we're looking at earthquakes, we need to find different ways to compare them, and there's a few different scales we can use to do that. The most commonly known is the Richter scale, developed in 1935 by Charles Richter. And what it does is it looks at the energy released, and it gives a rating, a magnitude rating of that earthquake that is exponential. So each level up is much greater. It's not just doubling, it's much 10 times greater also up the scale. So if we have a little look here, we've got 0 to 1, 2, 3, 4. Those are all deemed to be relatively minor. Once you get to kind of 5, 6, 7, those are the greater ones, and 8s and 9s are very infrequent, very rare, but when they do happen, are catastrophic. A different way of measuring earthquakes is on the modified Mercalli scale, and this is looking at the effects it has, or what was felt by people, the intensity it has. So here again you have numbers 1, 2, 3, 4, 5, 6, 7, etc. But it has a description. So level 1 is very gentle, it's detected only by very sensitive instruments. Level 2 felt by a few people who were perhaps resting and might have noticed just a gentle swaying. Number 3, noticeably felt both indoors, not necessarily quite so much outdoors, etc. Building all the way up to 11, where few structures remain standing, bridges are destroyed, fissures are open in the ground, pipes are broken. It's very much more about the impacts. There's another one called the moment magnitude scale. This is a more modern one, developed in the 20th century, and it's trying to bring out or address some of the problems with the Richter scale. This one is based on kind of looking at the total energy released during an earthquake. It looks at the fault, the length and width of the fault, the amount of slip, the material of the rocks involved, so it's kind of looking at a few more factors. But again, it kind of rates those earthquakes on a scale. So look, there's strengths and weaknesses between these. The Richter scale is the most well known, and when you find earthquakes have happened, that tends to be the scale that's used. However, these other two are worth knowing about because sometimes they will occasionally add that in as well. Right? Different measures of earthquakes. Okay, so what effects do earthquakes actually have on landforms and our landscapes? Well, they can be involved in the development of an escarpment. Escarpment effectively is like a steep slope or a cliff face that's separating two areas. And when you get plate boundaries, movement, particularly subduction zones, but you can also get these transform faults, that can be quite distinctive. You can find them in rift valleys. So very often that shaping of a rift valley, that magma upwelling causing the fracturing, and then the collapsing of the overlying plate will cause rift valleys to form, and you will see escarpments within these. So the East African Rift Valley is probably the best example, and you can see it in the photo here. 3b. Earthquakes generate distinctive hazards. Well, one of the first and probably the most straightforward is that an earthquake causes the shaking. The S waves cause the shaking of the ground, and that ground can be displaced. You actually have different things that can happen. If you've got a transform fault, you can get a strike slip where the plates just move past each other. If you have a constructive or destructive plate boundary, then you will find faulting. It may be a normal fault, it may be a thrust fault, depending on what's happening at that plate boundary. But you will find faulting, and you will see that particularly when you're looking at the landscape and any kind of built environment, as you can see on these roads here where that ground has been displaced. The ground will shake. Those P waves will cause shaking, but those S waves will cause large amounts of shaking as well. So shaking will happen. And sometimes that shaking will generate liquefaction. So liquefaction, it doesn't always happen, but it can, and it's where you find that the shaking of the ground destabilizes the soil, water comes into that, and it makes it much more liquefied. So it's very saturated soil, and as a result you can get subsidence. The shaking of the ground can also cause landslides in areas where you might have issues with soil stability or areas of high relief. You may find, again not always, but you may find that the shaking destabilizes it and causes landslides, particularly rockfalls. And again, this doesn't always happen, but sometimes if you've got areas of high relief, particularly fold mountains, you will find that where you've had snow built up, the shaking, particularly those S waves causing the shaking, will lead to the displacement of the snow and avalanches. Tsunamis can be generated too. In fact, tsunamis are generated quite regularly, but they tend to be relatively small in height. So each year, places like Japan might experience multiple tsunamis of a metre, maybe 2 metres in height. And that's where the plates have moved, and the movement of the plates have displaced the water above it in the ocean. And a tsunami is actually a series of waves, not just one, but a series of waves that move. Occasionally, you can get significant displacement, and that might generate large tsunamis, as you can see in the photo, which is an image of the Japan tsunami that hit. And here, with the drop in the land, this 10-metre wave came in and actually went over the sea wall that was there to defend this zone. As a result, those tsunamis can cause flooding, but actually flooding can be caused through other things as well. So any kind of landslide that might block a river channel or any dam failure in an area of high relief could cause flooding as well, all triggered by an earthquake. Okay, pause the video, have a little look at these key points. If you get it, tick them off green. If you're not sure, want to go back, amber, really don't understand, red. So rag your knowledge. Thanks for listening. Bye.